So here's my study guide. So here's the topics that we will go over. The programming topics we went over this semester were big Onotation, recursion, especially as it relates to trees. You're going to have tree questions on the final exam. And there's pretty much every single problem you do with trees, they almost certainly will use recursion if it's one of the traversals if it's a traversal you know. Sorting, insertion sort, no quick sort and partition, and no merge sort. Huffman encoding for data. Then we go over so that's the programming topics. For data structures, for the exam, you don't have to write any data structures, but you will need to know how to write code that uses them. So you've got your two types of lists. You've got your linked list and array list, and we're primarily going to be focusing on linked lists here. Know how long it takes to, the big notations for each of those. Know your stacks, your queues, your trees, and make sure you don't confuse tree with binary tree and binary search tree, right? And then heap. Remember that heaps are the way the heaps are always turned into complete trees. How to turn an array into a heap in O of n time. I don't know if I went over that with the evening class, but I don't think that's going to be on your exam, on the evening's exam. Hash tables. They don't really go into the final exam for the so the final exam for the common final doesn't really go into too much detail on how to use hash tables. But you guys are not taking the common final exam. You're taking my final exam. Which means that you will definitely get a nice big capstone question on hash tables. But also, you will have a question that basically goes over how to resolve open addressing. And know basically about all the stuff we just learned about graphs. So here are some sample finals from other institutions. I'm not providing a practice final for you guys. I'm providing 4 of them. I just happen to have written none of them, and they happen to actually be final exams that were actually given out at other institutions. So let's click on the first link and see where that leads us. So CSCI 102L data structure. So now some of them have gone over topics we will not have encountered. So if it sounds completely foreign to you, it probably is. Okay? So had a bunch of problems. This exam is closed book, closed notes, closed everything. Ours will be open everything. So yeah, open book, open notes. That's not really gonna, but honestly, don't waste your time with open book. Bring in notes. Okay. So let's see. What is the organizational property obeyed by all nodes in a binary search tree, i.e. the binary search tree property? So again, they're going to use different terminology. But if you know your stuff, you can realize, oh wait, so binary search trees, right? The big thing about binary search trees is that you got a root node, right? And then you got a left subtree and a right subtree. And all the stuff that's less than the root node that goes in the left subtree, and all the stuff that's bigger than the root node that goes in the right subtree. And then the final bit, which is that my left subtree and right subtrees are both binaries, also obey this property, right? That's what it comes down to a binary search tree. So let's see. Let's the key of a node. So in other words, the string stored in a node in a binary search tree be x. Also, we'll call this node x. Please give a definition of predecessor of x. Okay. So the predecessor of x. Oh, right. So by predecessor, they don't mean your parent in this case. That they're using the terminology of in-order predecessor, right? What is the predecessor of x? So what is the in-order predecessor of x? The next node that basically, if you print out in order, it's the guy who would come directly in front of you. So here's the more important thing. Given that you are at node x and you have 2 children, how do you find predecessor x? By traversing your children, right? How do you find your next in-order predecessor? Right? You had to do it for deletion, yes.
You go left once and then you keep going right
until you hit to right. That's your next in order. You find the biggest node in the small subtree. That's exactly right. So biggest node in your left subtree. So you go one to the left, all the way to the right. I haven't seen this in about a semester, so I have no idea what's on here. So I don't actually even recognize this stuff. So continuing part B, you have the successor of x, right? Which obviously is the biggest node the smallest node in your right subtree. The smallest thing that's bigger than you. How do you find that? Well, it's the reverse. You go one to the right, all the way to the left. All right. So why is it sometimes better to use a red-black tree or an AVL tree instead of a normal binary search tree? So we kind of touched on this a bit. Kind of. What's the big thing about trees that can happen to them if they don't? What can happen to trees that are bad?
They become less efficient because they don't balance.
They don't balance, right? And I didn't give you the definition of balanced until the exam, right? Which was actually not nearly as bad as you thought it would be. In that case, what's special about red-black trees and AVL trees then? We went over red-black trees, but AVL trees happen to be in the same chapter.
They self-rotate.
Yeah, they rotate around, and that does what? It balances them. They have self-balancing trees. All right, so ideal hash function and perfect hashing are not practical approaches for handling collisions in hash tables. Please name 3 practical and general approaches for handling collisions in hash table. Okay, so how can we handle collisions in hash tables? So what was one way that I taught how to build a hash table? I did a bunch of video lectures on how to build it, right? Using linked list, and what's that called when we use linked lists? It starts with ch. Anybody remember? Chaining, yeah. Some other people whispered it. So chaining, yeah. So chaining, where you have a bunch of linked lists and they essentially throw them in. Basically, each index holds a bunch of nodes. Bunch of entries, and just simply add it to the end. What's the way where we look for the next available spot? Anybody remember what that's called? So we get a collision, we look for the next available spot. What do we call that one?
Quadratic.
So there was the linear probing and quadratic probing, and those were strategies for doing open addressing. So we did open addressing. That's what it's called. Oh, we just learned this today. Under what conditions would you prefer to use an adjacency list to represent your graph over an adjacency matrix? You want a sparse graph. Yeah. What's sparse? What did we say what the cutoff point was?
A lot of edges compared to vertices.
Yeah. And the cutoff point is about 25%. Right? So let's see. So then we've got let's see. So here's a coding problem. I'll leave that over here. So pre-order traversal of a tree. So this one's a pre-order traversal of a tree. That's not too bad. Post-order traversal. Let's see. Insert this into a tree and insert 62 into the tree and result it. Single rotation. We didn't go over. We kind of went over rotations, but we don't really need to do that right now. It's not going to be on your final exam. Let's see. I think there was a good problem on this one. I'm just searching for it. Removal operations. The remove operation is not going to be on the final exam, but so here's a graph and its adjacency list representation. So do a breadth first search using this. So if you want to practice breadth first search there. Honestly, I'm going to move on from that one. And I want to come back to this final because I remember the reason I put this on my final was that this question I loved to death. So let's look at another final exam because I don't want to necessarily take away from all your practice. Right? But generally, all you really have to do is just Google like data structures final exam, and you'll either end up in like the with a data structures final exam or data structures and algorithms final exam. And depending on the institution, there's kind of a bleed between the two. Some stuff covered, like our course covers some stuff. Other courses assume you know big O notation coming in, and so they ask more advanced stuff about this. Okay, so question 1. Like here, question 1, they talk about like this is about like big O notation. Which ones are better? List them from best to worst, essentially. So that one you can figure out on your own. But here, consider insertion sort and merge sort. For each algorithm, what is the worst case asymptotic upper bound for each running time? Basically, what's the worst case scenario? What's the worst case runtime if your input's already sorted for insertion sort and merge sort? What would you expect the runtime to be if for insertion sort? So for insertion sort, what happens if the algorithm's already sorted? Sorry, if your input's already sorted, what kind of runtime do you get for insertion sort? Oh, event, yeah, it's already sorted. It will say, okay, insert the first item, insert the second item. That's free. The next item's free. The next item's free. The next item's free. What about if it's reverse sorted for insertion sort? It would be n squared. Yeah, so it's gonna take n steps to. It's gonna take 1 step to insert the first one, 2 steps to enter the second one, 3 steps to enter the third one, and so on and so forth until you get to the nth one. Ooh, we didn't talk about this one, but I think you guys can figure this one out. What if your input is a list that is n copies of the same number? So in other words, we had a million, say it was a list of 1 million items, and each item was 2. So what do you think the runtime would be? And this is actually one of those things where you would give me the runtime and you'd slightly have to argue it. It's O of n. Why is it O of n in your opinion?
I think it's the same as A.
Right. It's, in your opinion, it's the same as A. If it's less than or equal to, we don't have to keep inserting, right? We're done. And if it's only when if it's less than or equal to, if it's less than, that's when we have to push down. If it's greater than, if the item is greater than, then we can stop inserting the item. So for merge sort, what about all the answers for merge sort though? Merge sort, if you remember, is a very consistent algorithm. Yep. Yep, n log n no matter what. Merge sort always runs n log n. So, let's see. So, I'm trying to find some nice, good problems that, I mean, I'm going to make a second pass when we go through on Tuesday. Let's see. What other final exams do we have here? This one I think was, yep, this one's from Harvard. So I like this one because it had a lot of multiple choice stuff. So this was a practice final exam from their day's structures course. So, okay. Specify up to 2 answers. All right, so this one's a nice, good theory one. Suppose you have items A, B, C, D, and E pushed in order onto an initially empty stack. You then pop the stack 4 times, and as it's popped off, as every item is popped off, you put it into a queue. DQ 2 items from that queue. What is the next item that's removed from the queue? If you're trying to solve this in your head, forget about it. Don't bother with it. You've got paper. Use it, right? Okay? So we're going to insert A, B. I'm not even going to bother trying this. You know, there's no need to prove that you're super smart. A, B, C, D, and E inserted into a stack, into that order, right? Now we pop the item, we pop the stack 4 times, and as every time we pop a stack, we will be inserting the item into a queue, right? So E gets popped off and inserted into stack. D, C, and then B gets inserted, right? So we've popped off 4 items. As every item is popped off, we put it into an initially empty queue. So if 2 items are then removed from the queue, what is the next item that would be removed from the queue? So remove 2 items from the queue. Next item is C, right? This is one that we could just solve simply by doing the algorithm and understanding how it works. So if the binary tree is printed below, is printed in pre-order traversal, what will be the first result be? So we've got 5 different answers here. So first off, what in pre-order traversal, what is going to be the first node we visit? The root. Pre-order, meaning we do ourselves, then we do our children. So that means A and B are going to be wrong. So we want to focus on C, D, and E. Okay, so what's the next? So we visit ourselves, then we visit our left child, then we visit our right child, right? So the next number would be 17. So 6, 17, so we're looking at D or E. And then 9 after that, right? So it would be E. Let's look at this. A graph implementation that uses a two-dimensional array to represent the edges would be most reasonable for which of the following cases? So again, something we went over today. If we've got 1,000 edges to 1,200 nodes, 100 edges for 4,000 nodes, 1,000 edges to 10,000 nodes, or 10 nodes. Sorry, it's the other way around. 1,000 nodes, 1,200 edges, 100 nodes, 4,000 edges, 1,000 nodes, 10,000 edges, and 10 nodes and 20 edges. None of these, because a graph can only be linked by is represented by a linked data structure. So we can rule E right out, because if you've been paying attention today, you know there's two types of ways to represent a graph. They are adjacency list and adjacency matrix. An adjacency matrix uses a 2D array, which is what we're talking about, right? So this problem is obviously talking about a 2D array. Now, using a 2D array, those are best for either sparse or dense graphs. Sorry, I heard it. Dense. So 2D arrays are good for dense graphs. So a dense graph means that we're closer to to v squared. In other words, the number of nodes squared. So 1,000 nodes, the number of node squares is, it's 10 to the 6, so a million, right? So that would be good. So if we've got 1,000 nodes, we'd want around maybe a million edges, or 25% of that, according to our cutoff point. 1,200 is not, and 25% of a million. 100 nodes and 4,000 edges, that's 10,000 possible edges. 1,000 nodes and 10,000 edges, again, the million. And then 10 nodes, 20 edges, that's 100 possible edges. So the one with the densest one of these is 100 nodes with 4,000 edges, because we get 10,000 nodes. We have 10,000 possible edges, and 40% of those are represented, right? So B, it's the most reasonable for B, because B happens to be the densest of these things. Okay, so suppose you have a binary tree, and it consists of nodes that have a value, right? So most of these people, they don't use, I don't know why they don't use generics, but in this class, essentially they did it, so they assumed the nodes only held integers, they have a left and a right value. So consider the following method. I like this method a whole lot. Public static node mystery. So it's a method that returns a node, right? Root node. So if root.right is equal to null, so if this root node, so if the root of this tree or subtree does not have a right child, return the current root. Else, if it does have a subchild, if it does have a right child, return the function call of this node. Okay? So what does this so let's just think ourselves. What is this going to do? Right? This is going to essentially, if we call this on the root of a tree, right, it's going to go all the way to the right. Okay? So we are going to consult 3 supposedly tech-savvy consultants. And we get the 3 opinions about what the method does when passed a reference to the root of the node. So we know that basically what it does is that it returns the rightmost, it returns the rightmost node in the tree. And the answers they get back is that consultant 1 tells us that it returns the last node that would be visited in an in-order traversal. Consultant 2 says it returns the last node visited by a post-order traversal. And consultant 3 says it will return the last node visited by a level order traversal. Now, we didn't go over level order traversal. Level order traversal, because level order traversal is not something we do recursively. Level order traversal is the this. And the only reason I don't bring up level order traversal is that it makes sense to bring it up when we tackle graphs. So here is level order traversal. So level order traversal would return would give us the output of A, B, C, D, E, F, G. In other words, it would start the root, then it would go to the second level, and then it would go to the third level. Right? Now, this is actually what? If this is a graph, we'd call level order traversal what? Breadth first search. So the way to do it is that we wouldn't do it recursively. We'd use a queue. So we've got three consultants who say basically this thing returns the right, our analysis is that it returns the rightmost node. And they say that's the last node visited in certain traversals. So, okay. So, so which one of these people are right, regardless of the contents of the tree? So, in other words, which of these people is always correct? So, the last node in an in-order traversal, let's see, is always, the last node in the in-order traversal is always the biggest node, right? It's always the biggest item in the tree. And if we are always going to the right, we're going to be hitting the rightmost node. So consultant 1 is always correct. It would always be the last node in a pre-order traversal. Consultant 2 says it's the last node visited by a post-order traversal. The last node visited, now post-order traversal is go to the left, go to the right, visit myself, right? Where visit can be interpreted as process. So the root is always going to be the last thing visited. So consultant 2 is dead wrong. Consultant 3, it says that they return the last node visited by a level order traversal. Now, that works for the tree I have on the board, but we got to make sure it works in all cases. So let's say I remove the last node over here. The last node returned by a level order traversal would be F. The biggest node in the tree would be C. So our consultant in this case would be wrong. So my answer I would go with 1, unless I've previously misinterpreted the question, I'd say A. All right. So with a poorly chosen hash function, it is possible to have a situation in which the search time for a hash table of n items goes to what? So if we have a bad hash function, how bad can our search in a hash table get, right? We want it to be constant time, right? And that's what a good hash function will get us. A bad hash function would mean we get collisions all over the place, right? Basically, every time we'd get any possible collision that could occur, it would occur. So if we're inserting the nth item into a hash table, how many possible collisions are there? There's n minus 1 collisions, right? So it would take O of n minus 1 time, or O of n time. Now, depending on how we resolve that, it could actually take longer, like with quadratic hashing. You could like looking for that last empty space, but I'm just going to go with O of n. So let's go ahead and say, now I got the question one of the questions on your first exam from this final exam, which was, suppose you have a doubly linked list, which looks like what the nodes look like this, right? You've got n, you've got p, right? So which of the following is not a way to refer to the third node in this list? So you've got n and p so what's how can we refer to the third node? So p.next, that refers to the third node. n.next.next, that's the third node. p.previous.next does not refer to the third node. p.next.previous.next, that's the third node. And then n.next.next.previous.next, that's the third node. So it was C. All right, so this is a good scenario question, this one. A police department wants to maintain a database of up to 1,800 license plate numbers of the people who receive frequent tickets so that they can be determined very quickly whether or not a given license plate is in the database. So we're maintaining a database of people who are terrible drivers, and we want to know basically as quickly as possible, are these people in the database? Speed of the response is very important. The use of memory is also important, but not nearly as important as quickly as the response. So which of the following data structures would be most appropriate for this task? A sorted linked list, a sorted array with 1,800 entries, a hash table with 1,800 entries, 3,600 entries or 10,000 entries. Okay. In other words, a hash table which could hold up to 1,800 items, a hash table using open addressing using up to 3,600 items, and then a hash table using open addressing up to 10,000 items. Okay. So let's go through these one at a time. A sorted linked list would be kind of terrible because to search a linked list, you'd have to go through in order, right? There's no jumping around. You can't do binary search on the sorted linked list easily, right? Because you'd have to find the middle, which means you'd have to traverse to the middle. Then you'd have to traverse to somewhere else in that, and that would just that would kind of be off. A sorted array of 1,800 entries. Now that would be really memory efficient, right? You'd have only 1,800 spaces to use. And you can do it in log, and you can search for an item in log n time using binary search. So that's currently the leader. A hash table with open addressing using 1,800 entries. So we know that basically that this hash table, it's because it's pretty much 100% full. We're looking at basically getting collisions all over the place when we're looking for something, right? It's that parking spot problem. We're looking for an empty parking spot, essentially, and there's only one empty parking spot left, kind of in this example. I mean, there's nothing left, but we're searching for, like, our car. Yeah, that's a good way to turn the metaphor. We're looking for our car in a full parking deck, and we can't remember where we parked our car. It's going to take a while to find it, okay? Like, you think you think you left it over in this area, right? And if it's full, you just can't see your car, so you have to check a lot of spots, okay? Good metaphor there. On the other hand, if it's got 3,600 entries, right? In other words, it's only half full. You can probably find your car relatively quickly. In fact, we know that from when a hash table is half full. Basically, it takes the expected number of comparisons we have to perform is 1.5. In other words, we're expected to have either 0 or 1 collision. And with 10,000 entries, it's pretty much empty. So that's really wasteful. That's unnecessarily wasteful space. So we could get constant time lookup on this. We would expect to look basically once or twice for a license plate number, as opposed to a sorted array, which would take, let's see, well, it would be log base 2 of 1,800. So we can split that in half: 1,800 into 900, 900 into 4,500. 4,500 into 225, and we're at 3 now, which is now slower than the constant time we were looking at for the expected constant time we would get for D. All right, so a Huffman tree is constructed for a text document containing 5 characters. The character E appears the most frequently, and the character I has the next highest frequency. Which of the following could be a Huffman tree for this document? 1, 2, or 3, right? 1 only, 2 only, 3 only, either 2 or 3, or none of these. All right, so can 1 be a Huffman tree for this document? No, cannot be a Huffman tree for this document. What's wrong with this tree? Yeah, it has I and T in internal nodes. Your symbols have to be external nodes for a Huffman tree, right? So 2 and 3 both satisfy that. So let's see. So E is the most common thing, followed by I. So that means that E needs to be needs to use the least number of bits if it's the most common thing. So here it's actually taking the most bits up. So that's probably not a good Huffman tree at all. But here, too, E is using the least number of bits, and then says the next number of bits is the next most common character is I. So E is the most common, then followed by I. Yeah, that's a potential good tree. 2 is potentially a good tree for this. But 3 isn't. So the answer is B, only 2. So, why is 3 not? Because if E is the most frequent character, right, then we'd expect it to be somewhere near the top, because it would take the least number of bits. So this is just simply an empty binary search tree was constructed by inserting a sequence of items into an empty tree. Which of the input sequences will not produce this binary tree? So in other words, basically, can you construct this binary tree? I'll leave that one for later. let's see. Then hashing with linear probing. I'll leave that one for when I'm got that. I want to see. I'm going to finish up by trying a coding problem essentially. See, are there any good ones on this one here? Let's see. Yeah, I'm going to go over this one for the last 20 minutes. This one's one I'm very fond of. Okay. So you're given a text file that contains a week's worth of login durations for users on aludra.usc.edu. That's probably their servers at University of South Carolina, USC. University of Southern California, usc.edu. So each line of this file corresponds to a single login session. For instance, a line would contain a user ID, for example, Cheng W, followed by a space character, followed by the user's login duration in seconds, 3.14326. In other words, Cheng W was logged in for 314.326 for that login section. Your job is to compute and print out the average login duration for each user. For example, if the input file contains 2 login sessions for Cheng W, one at 314 and 326.36 and 204.7, then Cheng W should appear in your for 249.513 should appear exactly in your output once. The input file is unordered, and you may assume the input file is well formed, so you don't need to validate the input. Your output does not need to be sorted. Please write a partial C++ program, or you can do it in Java. You may assume the correct header files. In order to receive any credit, you must use 2 standard library maps, one to store the sum of the durations for each user, and one to store the number of login sessions for each user. All right, so we're using 2 maps here. They've given us kind of the answer here on how to do this. So for each user, right, there's to compute the average number of time, the average login duration for our user, we'd have to know 2 things. 1, for that user, how many times they've logged in, and 2, the total amount of time they've logged in for. So if I've done 3 login sessions of 1 hour, 2 hours, and 3 hours, then my total duration would be 6 hours, and then I've logged in 3 times, so my output would be, you know, it would be 6 divided by 3, which is 2 hours. So let's go ahead and try writing this up. So okay, so I've got a file. So unfortunately, I'm gonna have to parse it. So so basically, let's go ahead and say what's our input file called? So I'll just call it input. So scanner. So file f is equal to new file. Input.txt. Okay, and then scanner s is equal to new scanner f. So we're going to scan that file, right? So now, so now we got to read each line in the file. So while s, let's call this, I'll just call it scanner. While scanner dot has next line. So while there's still stuff to read from the scanner, string line is equal to scanner dot next line. Okay. So I'm going to read the line from the file, and then I'm going to split it up into 2 parts. Right? They said I can assume it's well formed. So string parts, right, is equal to line dot split on the space, and then we can do parts. We can say string user is equal to parts, the first part, and then the second part is equal to their double, which is their time is equal to double dot parse double parts 1. Okay? So we've got the amount of time this takes up. Okay? Now, what do we have to do? Let's see. So we've got the user input, we've got the user, and we've got the amount of time they logged in for that particular session. So if duration sum dot contains key, in other words, we're asking basically, does this exist as, have we seen this user before? Have we seen this user before? If so, then we want to add the amount of time we've seen this user. So duration, and I'll do that in one line because I'm fancy like that. Duration sum dot put user duration sum dot get user plus time. So I get the, so here with the duration, since I have duration sum inside of here, what I'm doing is I'm getting the amount of time I currently have, adding the amount of time that I've just seen to it, and putting that in to the thing. And then, oh, well, if they exist in the duration sum, I've already seen him, so I can go ahead and, you know, do the same thing for the amount of times I've seen them. Count.put user count.get user plus 1. So I've seen him an additional time, in other words, right? If I haven't seen him though, right? If it doesn't contain the key yet, then I should fix that. So I would just do. So I'll just copy this, and what I'll do is instead of putting in duration sum plus get user, I'll just do time. I've seen him for this amount of time, and I've only seen him once. Okay, and then I just do that for every line until I'm done. Okay, so now I've got the amount of time I've seen the user, and now I've seen the amount of time that I've got every user. So I've got the amount for each user, I've got the amount of time I've seen him, and I've got the amount of time that he's logged in. So now for string user in count.keyset. So in other words, for each user that I've seen, I'm going to now go through every user. I'll get the total time I've seen them. So double time is equal to duration sum dot get user, and then I will go through and then count int num logins is equal to duration sum dot get count dot get user. So we've got the number of times they logged in, we've got the user. Okay, and now I just need a third map for my output, essentially. I mean, actually not. He said just to output it, so I could just simply do an output here, so I don't need to store it anywhere. I don't think so. It's just, if I needed to store it and return it, I could put in a third map called averages, but I don't need to do that. System.println user plus and then the amount of time divided by the number of times they logged in, and that will output the number of that'll output each user and the amount of time they logged in, and they probably would appreciate it if it was separated by space. So there we go. That is the average number of time each user logged in to this program. And the hardest part about that was actually scanning the file, right? Which you don't really need to do. So it doesn't say I have to return anything, so I'm good there. Yeah, so that one was worth 15 points on their exam. I agree with that. It is a map questions are a bit extensive sometimes, but I mean they're good, they're useful, and they're very powerful tools, and you should learn how to use them. So we'll go over more practice exams and get ready for your final exam on next Tuesday. Okay. All right. So congratulations for making it to the end, by the way. So I'll see y'all next week.